Question 4. Compounds C and D are alkenes with the same molecular formula C5H10. Figure 4.1 shows the structure of C and D, and they are positional isomer. For A, part 1, give the systematic name of D. First, we need to find the longest carbon chain. So this is the first carbon, second, third, and the fourth carbon. And the double bond is between the first and second carbon. So we call but1-ene. Longest chain is 4 carbon, and the double bond start from the first carbon, so we call but1-ene. And we need to name the substituents. Now the substituents is the methyl group, and this methyl group is bonded to the third carbon. So therefore, we put 3-methyl in front, followed by the but1-ene. So this is the name for the compound D. Part 2. Explain why C and D do not show geometrical or the cis and trans isomer. For C and D, before we refer to this C and D, first you need to know what is the cis and trans isomerism about. In the organic chemistry, when we have the cis and trans isomer, the CC double bond, the carbon in CC double bond, they must have different groups, which means when this carbon now is bonded to one group and two groups, and they are different groups, and another carbon also bonded to two different groups, so this molecule or this alkene, it can form the geometrical isomerism. So if let's say now the larger group in this example is the CH3 and the CH3, if they are at different sites, so this we call trans. If now the CH3 and CH3 they are at the same site like this, so we call cis isomer. So it's always needs the CC double bond, and each carbon they must have different group, then it can form cis trans isomers. Now let's look at these the C and D. So from the C we know that the carbon in the CC double bond, especially this carbon, it has two same group, two methyl group. So C cannot form cis trans isomerism or geometrical isomerism. If we refer to this D, so this carbon has two hydrogen. So two hydrogen means two same group, and we know that this one also cannot form cis trans isomerism. That's the reason why C and D do not show geometrical or cis trans isomerism, because one carbon of the CC double bond, this one and this one, has the same groups attached. That's the reason why when there is a same groups, so therefore it cannot really form the cis trans isomerism. Part 3. Draw the structure of a molecule that is a positional isomers of C and D. So this is quite easy. The C has the double bonds here between these two carbon, and the D has the double bond between these two carbon. So we need to make another positional isomers. So we put the double bonds, let's say, between the third and fourth. So we can get another positional isomers, just like this. So we put the double bond here. So now we got a new positional isomer, and the name is 2-methyl but 1-ene. So this is first carbon now, second, third, fourth carbon. And this double bond also start from the first carbon, so it's but 1-ene. And now the second carbon has a methyl group, so it's 2-methyl but 1-ene. Part 4. Give the structural formula of the compound formed when D reacts with H2 in the presence of the platinum catalyst. So this is D. After it undergo hydrogenation, this CH2 get one H, this CH get another H. So therefore it will form this compound. So this hydrocarbon or this alkane. And you need to give the structural formula. Okay, so this one is the CH3, and these two groups bonded to this carbon. This carbon has one H, means this is CH. What you need to do is when they are two same group, so you just put them together. So it's a CH3 bracket 2, and these two CH3 bonded to the carbon, means this carbon, and this carbon has one hydrogen. So we just give the formula like this: CH3 brackets 2 CH CH CH2 CH3. So this is a structural formula. Part 5. C can form addition polymer. This is the C. Draw the structure of one repeat unit of this addition polymer. And this one is C. What we need to do is to open up the double bond, means remove one bond, pi bonds break, and add tails here. So when pi bonds break and add tails on the carbons, it will form this polymer chain. This is what you need to give, the polymer with one repeat unit. Make sure the tails, they are there, on this different side. B. The mass spectrum of C shows molecular ion peak at m/e equal to 70. This peak has a relative intensity of 48.7. Now the M peak has this relative intensity. We have to use this for calculation. And also given the M+1 peak is 2.7. So now it's given M and M+1 and their relative intensity. We need to use this information to calculate the carbon's number. Show that this information is consistent with the molecular formula of C. First, calculate carbon number using this formula. So it's 100 over 1.1. This is a ratio between the C12 and C13. So means when compare these two together, so this is their ratio, 100 over 1.1. And this one need to times the relative abundance or relative intensity of the M+1 over M+. And this one is given is 2.7 M+1, and this one is 48.7. Substitute these two and calculate, you get 5. Carbon number is 5, and already told you C is an alkene. Alkene has a formula CnH2n. So therefore, the molar mass of this C is 5 times, because it's C5H10 now. So therefore, it's 5 times 12 plus 10 times 1, so you get 70. This one is to confirm, right? It's consistent with the molecular formula of C, right? So what we get is 70. Part C. C and D both reacts with HBr. Part 1. C reacts with HBr to form E. Complete this diagram and draw the mechanism, include all the charge, dipoles, lone pair, and the curly arrows. So this one is C. When the HBr, this is the electrophile, when HBr approach the alkene, so this HBr, we say that this electrophile attacks the alkene. Alkene will donate a pair of electrons to this HBr, and the new bonding form between the C and H, and this HBr need to break. So it's break heterolytically. Of course, you need to put dipoles on the hydrogen and this bromine. Partial positive on hydrogen, partial negative on bromine. And you must draw these two arrows. Shows the bond formations here. The C will form new bonding with H, and the O bonding means the HBr need to break. Okay, after that it will form bromides here, and of course it will form carbocation, I mean the alkene. Follow the Markovnikov rules. We know that these hydrogens will bond to this carbon because this carbon has more hydrogen than this carbon. So this hydrogen will move to or bond to this carbon. When this hydrogen bond to this carbon, means now this carbon, the other carbon is charged positive because this carbon now is electron deficient. So it will form this intermediate then, and now this carbon with charge positive, the bromides that produce will attack this carbocation and form E. So this is a full mechanism and it's 3 marks. Part 2. D reacts with HBr to produce F. A chiral bromoalkane obtained, means the F is the chiral bromoalkane. Draw the structure of F. Before you put this answer, it's better for you to at least draft, see which one can form chiral compound. If let's say now the H is bonded to this carbon and the bromine bonded to this carbon, so we will get this compound. And this compound means this carbon has 1, 2, 3, another H is the last group. So it has 4 groups. So this carbon is a chiral carbon, so it's confirmed. Confirm this is the answer, means this is the F. If now hydrogen bonded to this carbon and bromine bonded to this carbon, so it will form minor product and no chiral carbon in these products. So we are quite sure that now the F, it should be this one. Okay, you just put this one to the box. Part 3. Explain why the reactions of HBr with C and D produce different major products. Before we discuss the one that on top, let's look at what is the products that will be formed. If follow Markovnikov rules, so it will form major products, and the carbon with more hydrogens will get the hydrogens from HBr. Okay, in this C, we know that this is a carbon that will form the new bond with hydrogen, and this carbon will form the new bond with bromine to form these major products. This one. For D, we know that this carbon has 2 hydrogen, so the hydrogens from HBr will bond to this carbon according to Markovnikov rules, and this carbon therefore it will bond to the bromine and it will form this major product. You see, the major product of the C and D, now they are different. So what is the main thing or the reason for them to have different major products? Then you need to understand how they add and what is the intermediates that form. Of course, you no need to really draw like this lah, right? Because it's just ask you to explain and it's 2 marks. I try to explain and let you understand why it's formed different major products. For this C, when it reacts with the HBr, when it undergo electrophilic addition, this carbon again has more hydrogen, it has 1 hydrogen here. So the hydrogen, if it's bonded to this carbon, so and bromine bonded to this carbon, so it will form the major product. And when the H bonded to this carbon, means this carbon is going to be a carbocation. So means it will form the first one, this one, and it will form tertiary carbocation. This is the most stable carbocation. Why? Because this carbocation has 1, 2, 3 alkyl group, and it will make this carbocation more stable. When it's more stable, actually it will form more. More stable means it's less likely to react with others, right? So you just need to remember, when the carbocation is more stable, then it will form more. When this intermediate form more, then it will form more products, means this major product. And of course, at the same time, it will form the secondary carbocation. If the hydrogens now, this hydrogen is bonded to this carbon, then this carbon must be carbocation, which look like this. So when this carbon is carbocation, we know that it just has 1, 2 alkyl group, so it's a secondary carbocation, which is less stable than the tertiary just now. For D, this one is compound D. When D reacts with this HBr, if let's say the hydrogens add to this carbon, so it will form this carbocation, because now this carbon must be charged positive, and this is the methyl group. And if let's say this hydrogen now bonded to this carbon, so it will form this carbocation, the primary carbocation. Okay, I hope you understand and you can see. So now the secondary carbocations that form is more stable than the primary here. Therefore, for D, if you use this intermediate to form the major product, means the bromide will add to this carbocation, will form new bonds with this carbocation and form these major products. This is why they have different major products. Means the C and D they have different major products. Now let's move on to this explanation. Okay, C will form tertiary and secondary carbocation. This one is what I explained just now. C will form tertiary and secondary carbocation, and we know that tertiary is more stable, right? Tertiary carbocation is more stable than secondary carbocation, as this tertiary carbocation has more alkyl groups, and this will give extra or more positive inductive effects. So positive inductive effect means when the electrons from the alkyl group push towards the positive charge, this we call positive inductive effect. More alkyl group, it has more effect, and it will let this carbocation more stable. So now the last one. D will form secondary and primary carbocation, as I told you just now, primary and secondary. And of course, the secondary will form the product, means these products, right? So that's why, because of different carbocation form, then the product's different. For C, again, C, because it's formed tertiary carbocation, then it will form this major product. And D will form the secondary carbocation, which is more stable than primary, then it will form this product. If you notice, actually the secondary carbocation for this C and D actually they are the same. But for the C, the intermediate, secondary carbocation intermediate will not be used, because there is a more stable carbocation form. So this one will form the products. Okay, I hope you understand what I said. If you're not clear, you can watch again. Okay, part D. C can be used to form H. So H is this one, C to form H. So this one is the ester compound. One possible synthesis of H, the ester, okay, in figure 4.5, different portions of C are used in the reactions 1 and 3. Some of the products are then combined to produce H. So I try to explain all together so you can have a clearer picture about this reaction. So now, reaction 1 and reaction 3, they all start from the same C. So let's move on to reaction 1, see what is formed. The C will form E after it reacts with HBr in reaction 1. So we know that this is the electrophilic addition. Means hydrogen add here and the bromine add to here to form the E. After that, it will undergo reaction 2 and form J. Then we need to know that what is the compounds that needed to form the ester. To form ester, we need two groups. One is the alcohol, another one is carboxylic acid. So we can form alcohol from this halogenal alkane. So we need to use sodium hydroxide. Sodium hydroxide in water. So this bromine will be substituted by OH and it will form this alcohol, means J. For reaction 3, as you can see, the C after reaction 3 is formed propanon. This is a ketone, and G. It's quite obvious that this C is undergo bond breaking, means undergo oxidation, and the CC double bonds break. When the CC double bond break, this part will oxidize and get the oxygen. So this one will form the ketone, the propanon, and another part, which means this part. So this is CH3, and this carbon will form COOH after it get oxidized. So it will form ethanoic acid. So it's formed two products. It's formed the propanon and the G. G is the ethanoic acid. So now we have carboxylic acid, right? And the alcohol. And we can let this G and J react. And this reaction, of course, is the esterification. Means to form ester. Esterification, it needs to use concentrated H2SO4. And this is how it reacts. Means this is a condensation reaction. So the name is acidification. The type is condensation. The COOH, OH from COOH and the H from OH, now if you removed and form the H2O, and of course the new ester bonds form, right? So this one COO after the reaction. So this one is the whole reactions which is from C to form the H. And this is the table, and you just need to fill in the blank. For reaction 2 again is the substitution from E to J, means from this one. Reaction 2 from E, this haloalkane, to the alcohol. So we need to use sodium hydroxide in the water. So you just put sodium hydroxide aqueous. And for the reaction 3, we know that is the oxidation, the CC double bond break. So we need to use hot acidified concentrated KMnO4. Acidified must be there because in order for this KMnO4 to oxidize others, acid must be used. For reaction 4 is the last reaction, this acidification. So we need to use this concentrated H2SO4. That's all for this question. Thank you.